Hello everyone and welcome back. In this video, I'm going to be walking you through the full derivation of the equation of motion for simple harmonic oscillators. Simple harmonic oscillators consist of a spring attached to a mass. The spring has stiffness K and the mass M. And to cause simple harmonic motion, we must displace that spring away from equilibrium by some amount x. We either compress it or we extend it by that amount, and the spring will always put up a force, a restoring force, of size k times the displacement amount from equilibrium. So this force here is variable. It's going to change in size based on how far away you are from that equilibrium position. Now, so far in physics, we've been dealing with constant forces, ones that are not changing with time or with position. But this guy here seems to be not only dependent on position, but again, that position dependency can be translated into a time dependency as the oscillator goes back and forth and visits similar places at predictable times. We can do the translation. However, again, I want you to understand that we're just dealing with non-uniform forces anymore. And this is the first time that students typically see such non-uniform forces. What's the problem with them? The problem is that when you have non-uniform stuff in physics, they invite over the use of differential equations and integration. In this case, it's going to be a differential equation that we can solve. So, dynamically, this is not a complicated problem. If we translate it to a free body diagram, it looks like this. You basically have three forces, two of which are irrelevant to the problem, the normal and gravity, namely. Kx is the only one acting in the acceleration's direction, and that's pretty much it. We want to make sure that we indicate that Kx is a restoring force by making the choice of positives pointing always away from where Kx is pointing at a certain snapshot that we're analyzing. So, how does this look like if we start analyzing it? Well, if we do the x component where the action is actually happening, we do have an acceleration there, and the only force in the x direction right now is that negative kx. So we put it down. Now for the acceleration, we must notice that a and x are related through a second time derivative. I can always rewrite acceleration like so. And now that I have it like this, I would like to put all the terms on the same side to judge what kind of differential equation I have in my hands more easily. So if I do that, I have md squared x dt squared plus kx equal to 0. And one more thing I want to do is, when I have this at hand, I want to divide everything that multiplies the highest order of the derivative. It just makes it easier to see what's going on. So right now I'm going to have, if I do that, k over m times x here. I can highlight the terms here that depend on x, which is changing with time, right? And I want to notice the type of equation I have in my hands. Namely, this is a second order because of the highest order here being 2 on the derivatives. Linear, because I don't see, for example, a term like x squared here. Ordinary differential equation with constant coefficients, because here the coefficient is 1, here it's k over m, which is a constant, and here the other side is just 0. Now, those equations typically have exponential solutions, and we usually try to guess the solution as an exponential of the form e to the rt. If I take the double derivative of this right now, what I end up getting, you can very easily see I will get r squared e to the rt. Before I move on, one change we want to make now so we avoid having to make it later, whatever multiple here, whatever constant is multiplying that x in simple harmonic motion, we denote it with omega squared. This is by convention, and it is because this constant has direct relationship to the frequency of our simple harmonic oscillator. So Having now the assumption here about what the solution is going to be, we plug it in, and we basically get r squared e to the rt plus omega squared e to the rt is all equal to 0. Then we can factor out the e to the rt and be left with this term inside. All of this is set to 0. Here you have two options. Either you have that e to the rt is actually going to be 0, or that r squared plus omega squared is going to be 0. Now the left one means that there is no oscillation taking place, so this is unphysical. The right one is just setting a bunch of constants equal to 0, right? So this can be hold true. So what is r after we solve this? Well, quite clearly, if we rearrange here, we're actually going to get an imaginary value. We're going to get plus or minus I omega. So this is our r. And this is a complex number. We can write it in standard form, for example, a plus ib. And if we write it in standard form, we get here 0 plus or minus I omega. This is the complex number that we get for r. What does this mean right now? Well, if you've studied differential equations at all, and you've seen this class of differential equations, you know that there's only 3 scenarios that you can get based on the value of r here. 3 scenarios for x of t. And those scenarios I've outlined a little bit further down here in the problem. So you can have r values that are real numbers and they're repeated, the roots are repeated, in which case the form of x of t would be this. You could have r that are unique, in which case the x of t function would look like this, that it would have this form. And then you could have r values like in our case that are complex, and in this case the x of t function will look like this. Obviously we are in the third case, so I might as well just copy that and go and paste it upstairs, and we can continue our derivation. So here's my official x of t. We can see here right now what the value of a is. It's just 0. And the value of b is simply omega. So I make those substitutions immediately in the form that I'm going to have for x of t. E to the 0 is simply 1. So, this term just vanishes. And you're left with a e I omega t plus b e to the negative I omega t. Now, the next thing we must notice is that, exponentials of this form, this is a complex expression, complex number expression. And, it's a synopsis of writing cosine omega t plus I sine omega t, if you're familiar again with complex numbers. This is a synopsis of this. So, if we want to express this in terms of cosines and sines, this is how we would open it up. Now, what about this guy? Well, that guy, all we have to do when we have that negative there is we have to change the arguments of the cosines and sines to a negative as well. So I'm making that substitution right now. Then we can abuse the nature of cosine and sine functions. Namely, cosine functions here are actually even, which means they don't really care that you just changed the sign of the interior. They're going to give you the same value as the unchanged interior. But for sine, when you flip the interior sign, you're going to get the opposite value of what the original would give you. So you're going to get negative I sine omega t over here. And this is a way, again, you can express both of these guys in terms of cosines and sines. Okay, so maybe I should just substitute right now into my x of t this information. So I have a times over here, e I omega t, which we discussed is going to be this guy. We close the bracket, and then we add b, and we open the bracket, and we're going to plug in what this guy is right now in terms of, cosine and sine of omega t. There he is. And then we close the bracket there, The next thing I want to do is group like terms over here. So I'm going to take together the cosine omega t terms. That means I'm going to have a plus b if we factor properly times cos omega t. And then for the sines, I'm going to have plus a minus now b, you can see the minus here, times I times sine omega t. And I want to point out the fact that these guys here are constants right now that I'm highlighting, and I can replace them with one single name. Call them whatever you want. You can call them C1 and C2 right now for convenience. So we've established that this x of t function is going to have a form that has a constant times cosine omega t, some constant C1, and then another constant called C2 times sine omega t. It doesn't matter if these constants are, real or complex. It doesn't really matter. It just matters that they are constants. So I've actually done this substitution, you can see over here. And now I'm getting pretty close to what you've seen in your standard physics textbook. So how does this go away? Because usually on a physics textbook, they show you that x of t is going to be some constant. We can call it here for our purposes. Let's call it d. Some constant d, and then cosine of omega t plus a Greek letter phi that stands for phase. So how can you jump from there to the bottom? Well, we can prove that it is possible to actually cross-reference these two forms of x of t. Let me show you how. You can open the cosine here using the compound angle formula for cosine. So if we do that, if we open this up, we get cosine omega t times cosine of phi. And then we use the opposite sign here of what is in the argument. So minus sine of phi, omega t, and then sine of phi multiplying it. And now I can go ahead and actually distribute everything, but I'm going to write everything in a very specific way. So I'm going to write d sandwiched together with cosine of phi and then cosine omega t. Sorry about that. So right there. And then I'm going to write d sandwiched with sine phi and sine omega t afterwards. Why am I doing this? I want to point your attention to what the first constant here is really. Think about this for a second. Maybe pause the video and try to think why I've organized my my x of t function like this right now. Maybe you can see some connection if you pause the video and think about it. If you have done so and you're coming back, I'm just going to tell you, basically right now, this constant down here is the C1 from this form over here, right? It's the C1 from before. And then the other constant over here is the C2 from before. So what does this mean? It means that if we want to write this form of x of t in this form over here, we can establish connections right now, what the constants are going to be. So basically we are going to say C1 is going to be d cos phi, and then C2 is going to be d sine phi. And where do I go from here? Well, one thing you might be able to notice is that if I add these guys in quadrature, so I do, for example, I'm going to say here note. So if I do right now C1 squared plus C2 squared, I get d squared cos squared phi plus d squared sine squared phi. And obviously here I can just factor the sine and the cosine. And we know very well that this is nothing more than just 1. So basically what I'm telling you over here is that you can determine d right now if you take the square root of C1 squared plus C2 squared. Done and done. So we found a connection between D of the new form that we want to express x of t and the constant C1 and C2 from the old form that we had earlier. What's missing? Phi. How can I get phi? Well, if you can see again the relationships between C1 and C2 and the constants of the new form, we can go ahead and divide them. If I go ahead and divide, let's say, C2 by C1 right now, you can see that I get d sine phi divided by d cosine phi. The d's will drop over here right now, and you're going to get that tangent of phi is simply C2 over C1, or that phi is nothing more than tangent inverse of C2 over C1, which connects the last variable of our new format, so the new variable again here, against those of the old format. So we've established right now that we can change. I want to again explain what happened here. We've established that we can trade forms over here. We can express this guy in terms of that guy. And we can find what the constant d is, for example, in terms of C1 and C2 in the following way down there. And then we can do the same for the other constant. On the other constant that's found in the new form, we can find what phi is in terms of C1 and C2 in the way that you see down here. So we know that we can do the switcheroo between the double cosine and sine that you see and the single trig function of cosine. So that allows us to conclude that we can express x of t as some constant d times the trig function of cosine omega t plus this phase. And we can supplement again what these d's and phi's are. And this is where you basically stop in a physics textbook. This is what you will see being presented to you, and now you understand where it comes from. Further from here, what you can do is start taking time derivatives right now, right, and jump to the velocity expression and the acceleration expression for the simple harmonic oscillator. For example, v of t here, if we take the time derivative of this is a constant, that's a constant, that's a constant. So when we take the derivative of this, we end up with negative omega times d sine now omega t plus phi. And then if we go one more and take one more time derivative to get to the acceleration of the simple harmonic oscillator, we get the derivative of sine here is just going to be cosine, no negatives popping up. And then that omega is going to pop outside. So you're going to get minus omega squared d times cosine omega t plus phi. And then from there, you can establish various relationships. For example, you can divide over here, if you'd like, the acceleration equation by the position equation. And as you can see, if you do so, look what happens if you divide these two, right? You only have left minus omega squared. So you can relate, again, acceleration and position via the use of omega squared, which is really useful. So this is what I wanted to cover. I wanted to show you how you can get from first principles onto the equation of motion for a simple harmonic oscillator. If you have damping, if you have friction, there will be different forms, again, that you're going to have for the solution. There's not going to be, for example, for damping, you're going to have an exponential, a decaying exponential, not a trig function. And if you have other forces acting on the system, like, for example, someone's pushing the simple harmonic oscillator, or you're trying to model a pendulum that oscillates back and forth, what ends up happening is those changing forces, the forces that are involved in the pendulums, they're going to be reflected in the value of omega. So omega is going to be different for those objects, and we will see in future videos how that is. So for the simple harmonic oscillator, omega is simply root of k over m. But for more complicated oscillators, you might have, like, for example, you might have over here something attached to a wheel over here, something that actually rolls back and forth over here. And the omega is going to look very different for that object, but the equation of motion is still going to be actually a cosine. It's just that the omega is going to change. So you can see classes of oscillating objects, and the big things that can vary are the actual damping and the boosting. So again, we'll see more of this in the future, but I hope this covers enough. Where did this actually pop up from in your textbook? That's all I wanted to cover in this video. Thanks so much for watching, and I hope this has helped. If it has helped, consider subscribing.